Hi, I am Shivji from Nutanix, and together with Tarun, we will be presenting a brand new talk where we will talk about keeping on top of hybrid cloud usage with Apache Pulsar. I am a staff engineer at Nutanix. I am an Apache Pulsar contributor for over 3 years now. I lead the cloud data platform team at Nutanix, where we are a team of 7 people providing open source data tools as a service to support multiple Nutanix products. I love distributed systems and I am an open source fanatic. I am a complete data nut and I love databases, streams, analytics stores, etc. And over the years, I have contributed to MySQL and Pulsar source codes in addition to some others. You can find my LinkedIn URL there, and then I'll open up to Tarun. Tarun, can you introduce yourself, please?
Yeah. Hi everyone, this is Tarun. I work as MTS3 at Nutanix. I love distributed streaming frameworks and I have written multiple articles on achieving fault tolerance by using these frameworks. And I generally write more about software technologies that developers use day in and day out. And I am exploring Apache Pulsar for past couple of years.
Thanks, Tarun. So this is the legal disclaimer where we basically mean that whatever we present here are our own views and we do not represent the Nutanix Corporation. You can read through this, but then I'll now move to the main content. So what do we do at Nutanix? Infrastructure basically comes in two variants broadly, which is on-prem and public cloud. But Nutanix actually unifies the simplicity of public cloud with the performance and security of private cloud. And whether you are on-prem or you are a hybrid infrastructure user, we will ensure business continuity for you through centralized management and one-click operations, be it upgrade, be it disaster recovery as a solution. Our USP actually is one-click operations, which our customers absolutely love. And by the way, we have more than 20,000 customers, a lot of which are in Fortune 500 companies. You can see a few logos here, but there are a lot many that you can look at in our documentation in the link that you see at the bottom right. Moving ahead to the agenda. So what we present here is the need for multi-cloud and hybrid cloud, the challenges that you will face using multiple clouds or on-prem together sort of there. And then we head over to architecture for a single pane of view for looking at your infrastructure. Then we will head over to Flink-Pulsar connector, where Tarun will pitch in, and then also present specific features of Apache Pulsar, which we have leveraged to keep the site running for us. And we will finish it up with the challenges we have faced in production while we have been running this in production for close to 4 years now. So starting off with on-prem infrastructure, let's say you make on-prem infrastructure, what do you need? You need compute, you need storage, and you need network. And together with it, you make some capacity. And by the way, you have a lot of control over the resources you own because you own it end to end. The other part of it is that your server usage should be predictable because extending infrastructure, getting more capacity, be it storage, compute, or network, will require a cycle of buying hardware plus licenses. But the amazing thing about private cloud infrastructure is that because you own the whole stack, the data center is completely under your control, your cost is actually quite less. Cloud, on the other hand, is incredibly costly. If you look at the biggest spends of the startups today, apart from the employee salaries, the infrastructure cost is something that burns a lot of money. And given the times that we are living in with layoffs and stuff, and then recession looming over our heads, I think we don't need to sort of really justify why saving infrastructure cost is such a great benefit against, going the other side of layoffs and things like that. And then you obviously have an enhanced security. You can literally make a dark cloud in your own data center by limiting your network. On the other hand, if you look at public cloud and you want to make your infrastructure there, you can do that by renting servers from any public cloud provider. It could be AWS, Azure, DigitalOcean, Google Cloud, and there are a lot many of them. So you can again get the required amount of compute, storage, and network. The great thing about public cloud is it's fast and easy access to set up your infrastructure. And the pay-as-you-go model is actually the best thing, I think, in public cloud model, where you can rent something today, maybe next week you want to use only half the infrastructure, and going ahead for one day, you want to sort of probably use 4 times the same. And that doing that is literally sort of click of a few buttons on the public cloud dashboards. What if though, you could make an infrastructure leveraging the best of both worlds? So you have your own data center as well as you get something from public cloud. And in your own data center side, you can only keep that much capacity which you need throughout the year. And let's say you have a holiday sale, right? Like let's say a Christmas sale or something, and you need more infrastructure only for that period. So for that small amount of time, maybe for a week or so, for a couple of days, you can get more infrastructure from public cloud, and you then pay rent only for that small amount of time, which is what we call cloud bursting. So you can actually spill over your infrastructure requirement to public cloud and then stay in own data center when that is enough. The second use case for hybrid cloud is disaster recovery. And by the way, we would love to tell you that Nutanix has an amazing Nutanix disaster recovery tool, which you can read more about in the link below. But being more distributed across geography means that you are more available in the event of a disaster. Your site never goes down, because if one site goes down, you can always get it live. In fact, you can get it live automatically using Nutanix disaster recovery. And the replication and disaster recovery are really effortless across sites using this tool. You again get single click failover, and you have automated recovery plans that you get with this. So if I get a pen to show you this, you have a site A in, let's say, one part of the geography. You can replicate your infrastructure to recover in the time of a disaster on another on-prem site. But if there is one corner of the world, some continent where you don't want to send your people to maintain your site, then you can only rent public cloud in that part of the geography. So then your cloud effectively allows you to spread out everywhere and keep you more available in the event of a disaster. If your maybe one side blows, maybe this blows down, and then you can use the other one, which is based on public cloud. With multi-cloud, you can actually also combine the best of different clouds. So you have AWS, you have GCP, and Azure in this example. AWS has been there for the longest time and is really the sort of backbone of a lot of web applications that run at humongous scales. So you can leverage the bare metals from there. S3 is something that works quite amazing. For big analytics, I think Google really is the best. The spanners and the BigTables of the world started out there, and Google actually provides that out of the box as a service on the Google Cloud, so you can leverage analytics tools from there. If you have some part of the infrastructure which is a Microsoft product, you can get it from the Azure, let's say Cosmos DB or something. But then there are no free lunches in the world. So if you go for multi-cloud or hybrid cloud, you are going to have some challenges, right? And the first of them that I think is a huge challenge is the lack of unified visibility across cloud boundaries. In one cloud provider, you will get tools to visualize things, alert and stuff like that. But across cloud boundaries, in one single pane of view is what you want to have your visibility, and that is difficult. And that is where this architecture that we propose going forward is something that will help you get to this problem. Combining infrastructure from different providers is actually generally very difficult, because if you get some infrastructure from AWS, let's say the bare metals, you get BigTable from Google Cloud and stuff, or maybe you have an RDS from AWS again. Combining all of this together is difficult. One guy is going to have its own definitions, its own limitations. To combine it with the other guy with its own limitations, you are going to find it slightly complex. Then you also have to keep on top of every leak. So today, any leak is something that people are looking out for, and they can really exploit that. Let's say you have a simple example where somebody opens the port to public by human error, and you really want to be on top of it to make sure that you don't violate your compliance rules. To make auditing span across multiple clouds, including the private cloud, we again sort of help you with tools at Nutanix. And then there is the problem of skill gap, where your IT team actually needs to have the skill of AWS, Azure, Nutanix on-prem, the Prism UI and stuff like that. So instead of knowing all of that, your IT team can actually, with our tools, only look at this one single pane in the Prism UI, where we put all the monitoring together. And in that context, I think it's amazing to look at this tool, Nutanix Cloud Clusters. Again, you can read more about this in the documentation, but what we have here is that all your clusters, whether be it on-premise or public cloud, that can be operated as a single cloud. You have seamless application movement across clouds without any code change. So looking at this diagram, actually, this is the pane that I am talking about. It is one pane that spans through private cloud as well as AWS in this picture. And then you can have other services from Azure or any other cloud. Right now, we support AWS and Azure along with the Nutanix private cloud. But your application really builds on top of the infrastructure that you get out of our Prism UI. And then you can move infrastructure that you are using for your application seamlessly with our Nutanix Cloud Platform solution. And by the way, you get on-demand capacity bursting. Capacity bursting is something that I explained in the previous slides. And then there is single-click disaster recovery that you get with Nutanix solutions. Now, we will switch over to architecture that can support a single pane of view. And a bedrock of this architecture is actually Lambda architecture. So I'll start with the Lambda architecture, put some color into it, and then to sort of take it towards the end, I'll involve Tarun here. So Lambda architecture basically is an amazing thing that helps us unify the advantages of batch and stream worlds. Both of them have their own benefits, and your infrastructure can be different for them, but you can sort of serve a wide variety of use cases using Lambda architecture, and we can withstand a lot of faults as well. So if you look at the batch layer, it's amazing if you need high precision, but perhaps your latency is sort of something that you can play around a little bit with. And think about the Hadoop world, where we had a lot of involved algorithms, and we used to require a lot of compute capacity. That's something that can give you a good notion of the batch layer. In the speed layer, you can look at some of the latest tools. Databricks actually provides a lot of them. But what you do in the speed layer actually is that you trade precision for low latency, because your use cases like fraud detection and all are something that has to be real time. You can't really trade off with latency. Maybe you can miss 1 or 2 events when you look at n number of events, but sort of whatever you need to catch really, really quickly so that it doesn't affect more of your customers. And in this world, actually, you can use Pulsars and Kafkas of the world to store your data streams, and you can process them with Flink or Spark kind of a tool. Adding sort of a picture to represent the same, you get new data, or you can sort of get the complete snapshot of all the data with the new data, and then you can move it through batch layer as well as speed layer. In the speed layer, you will get a real-time view. In the batch layer, you can get your complete data set. And with the batch layer, you can optionally add a service layer, and then your queries can actually span the batch layer as well as speed layer. So some of your queries that power your application could be based only on the batch layer, or some other queries could be based out of only the real-time layer, or you can combine queries from both the sides, and then the results sort of together serve your application. So adding more color to the same things, which is data, batch, and speed layer in the next slide, I'll show you that we have Azure scrapers, we have AWS scrapers, and we have Nutanix scrapers built in Nutanix, and we sort of scrape all the data and stream it through the batch and stream layer, where Pulsar and Flink are actually an amazing match. So Pulsar will provide you a way to store data and query it via the streaming APIs, or you can use something called the segment APIs, or the sort of ledger APIs, to actually get it in the batch form. In Flink, again, it is a tool that provides you capacity to do batch as well as stream. So combining Pulsar and Flink, you basically get storage and compute for both streaming and batch kind of applications. And once you have stored and processed your data, you can really store the summary in any sort of backend store, which is going to power your query layer. And that could be a Postgres kind of a RDBMS, a graph database, or an analytics store. So extending that again, we have our scrapers, which get a view of the usage of the cloud. In this case, you get a view of the Azure infrastructure that you're using. Here you get a view of the AWS infrastructure that you're using. And here you are essentially trying to make a snapshot of the Nutanix infrastructure that you are using. And going ahead, you combine all the inventories and stream it into Pulsar. You move it through Apache Flink connector to Apache Flink, where you can join different streams or different topics in Apache Pulsar, and you can sort of process this together with a custom code written in a Flink operator, or you can fire a streaming SQL. You could do a complex event processing or CEP kind of a use case, and then you can flow it back to Pulsar again to maybe process in multiple hops. Or if you have already got your summary that you're happy with, you can send it through to your backend data stores, which your UI could query, or even put it in a graph store, Elasticsearch, a Druid, a Postgres, or MySQL, or anything you may wish to support your application. For Azure, we use activity log to get a lot of data. For AWS, we use CloudTrail. For Nutanix, we have in-house scrapers that combine well with our own VMs. And that's how we sort of send data to Pulsar. And here I'll hand over to Tarun. So Tarun, you can start sharing and continue on with the architecture.
Thanks, Shiv. As Apache Pulsar and Flink constitutes to the heart of our architecture, over next few slides, I will introduce you to Apache Pulsar and Apache Flink, and I will take a deep dive into Flink-Pulsar connector. For the other slides, I will take you into the features that we use in Apache Pulsar and challenges that we have faced with Apache Pulsar and Flink, a system as a whole in our production. First, let me introduce you to Apache Flink. Apache Flink is a true stream-based distributed processing framework, unlike systems like Apache Spark, and it uses the same framework for both batch and stream processing, which makes it a unified batch and stream processing engine. Also, unlike traditional event-driven applications with separate application computations from storage, Flink uses its local states for all its computations. which makes its computations much more efficient and faster. And Flink periodically stores this data in a persistent storage to achieve fault tolerance. This true nature of Flink makes it efficient for ETL applications where it can read events from systems like Pulsar, ingest into Flink by using Flink-Pulsar connector, and do enrichment or the computations that you need and trigger further events, or even it can write this data back to Pulsar so that other applications can consume this data. And Flink uses this Flink-Pulsar connector to read events from Pulsar and write these events back to Pulsar. Creating a Pulsar source through Flink-Pulsar connector is easy by using a builder, where you need to provide service URL, which points to the Pulsar broker cluster, and cursor's starting position, which can be earliest in your Pulsar queue or oldest in the Pulsar queue, or even you can provide message ID from which you want Pulsar to retry the data. You need to provide set of topics from which you want Flink to consume events and subscription name for your consumer group. Also, Pulsar provides 4 types of subscriptions, for example, exclusive, failover, shared, and key shared. The advantage with Flink Pulsar connector is it helps you to set the right subscription for your requirements. Also, you can set the Pulsar source to read from multiple topics or multiple partitions from the same topic, or even you can use regular expressions to match all the partitions of a topic. You can use Pulsar deserialization to deserialize the bytes that are transferred in the form of Pulsar message to Pulsar schemas. You can use this deserialization to achieve clean code too. As we understood Apache Pulsar Flink connector, let's take a deep dive into our architecture from Flink Pulsar connector perspective. We have a lot of data producers like from Azure, AWS, Nutanix. We even have external data producer that produce events that we could not collect. Now, all these data producers push data to Pulsar. Now, our data can be an event. For example, update virtual machine that is collected from your AWS log trail. Or it can be an inventory, which is the actual EC2 instance that got updated and metadata about that EC2 instance. And now we have our Pulsar cluster. We have our Flink cluster, which have a lot of Flink jobs which are consuming events from this Pulsar. Now, let's suppose there is an AWS stream job which consumes events from Pulsar, and there might be AWS batch job which consumes inventory from Pulsar. And batch job might be triggered once in a day, and stream job might be triggered once in 10 minutes. Let's take a deep dive into one of these Flink jobs to understand what happens inside the Flink. Every time we get an event, we need to enrich event. For example, as we discussed before, let the event be update virtual machine with particular ID. We need to find the metadata of actual virtual machine and append to this event so that we can do further processing on top of it. Once we enrich event, we run audits on top of the event. An audit can be, is your Azure disk encrypted, or is your AWS EC2 instance have public IP assignment? We run a lot more complicated audits than this, but at the end, we run audits on our inventory and generate findings so that once we generate findings, we can sync both inventory and findings to our databases. Initially, we started with Postgres, but with time, we realized that there is unique relationship between these inventories that our customers are interested in exploring. For example, find me all the disks that are attached to a virtual machine, or find me all the policies that are acting on a virtual machine. So we have developed our own custom query language that sits on top of Neo4j so that customers can write simple queries and we query Neo4j to retrieve the data. Once we do all this processing, we push these issues back to Pulsar so that our notification service can consume these findings that we generated. And our notification service will notify users through email, Splunk, or even webhooks. It depends on the rules that customers have configured in our application. As we are using Apache Pulsar for quite a long time, there are a lot of features of Pulsar that we take into advantage. First is partition topics. As we know, in Pulsar, one topic can be managed only by one broker. But at the scale we operate, we need much more throughput. That's when we use partition topics. I will discuss about this in depth in my later slides. Next, unified messaging model. There are a lot of queuing systems like RabbitMQ and streaming systems like Kafka that are available in market. But Pulsar, being a unified model, helps us to develop products based on one underlying system as a whole. I will discuss about this in depth in my later slides too. Next, Pulsar schema. Pulsar built-in schema management helps both producers and consumers to coordinate on the Pulsar schema for the topic. This coordination happens in the broker itself, which helps us avoid external schema management tools. Also, multi-tenancy. In Pulsar, all the data in your topics are stored in a hierarchical way. So you have tenant, namespaces, and then topics. This will allow us to configure policy controls over multiple layers. For example, the maximum storage that you can have for a namespace or time to live for messages in a topic. Also, multi-tenancy helps us to isolate multiple tenants, which will improve performance of your tenants. Also, the rich set of Pulsar Flink connector that we have discussed before, this will help us to use both Flink and Pulsar features to their fullest. Now let's take a deep dive into partition topics. Let's suppose you have a producer which is producing events at the throughput of 300 messages per second, and it wants to save all the events to one topic. But you have sized your Pulsar cluster such that one broker can only manage 100 messages per second throughput. If you take these configuration to your production, you will face a lot of issues. This configuration will create back pressure on your producers, and now your Pulsar cluster is actually unstable, and your producer need to do a lot of retries to send a message. And there is nothing much that you can do because you cannot scale your Pulsar cluster, you cannot scale your brokers horizontally beyond a limit. That's when partition topics comes for rescue. In partition topics, what we can do is we take the data that a producer is pushing, and you can make sure that all the data is mapped to one of these three partitions. And if we have configured our Pulsar cluster with 3 brokers and each broker has a 100 messages per second throughput, let's suppose each broker picked up one partition, then your problem is solved. You get 300 messages per second throughput, all the data is produced to one topic, and you are utilizing 3 partitions. We are happy. But there is a catch here. With partitioning, you will lose ordering of events across partitions. In our product at Nutanix, we need ordering of data for each customer. So what we do is, instead of using round robin strategy for customer message distribution, what we do is we hash our customer ID and make sure that all the events for a customer are sent to one partition. In this case, we might not achieve equal throughput for each broker, but this will help us to achieve the scale that we need, adhering to the ordering constraint that we have. Next, Pulsar, being an unified streaming and queuing model, helps us to maintain one copy of data and satisfy the needs of multiple consumers. So it is like combination of RabbitMQ style queuing and Kafka style streaming. Let's take an example. We have a Pulsar producer which is producing events to 3 partitions. We'll pick one of the partition to dive further. So let's suppose the messages that it is producing is M0 to M4 in this order, and you have a Pulsar, you have a consumer which is consuming events from Pulsar topic, and it needs all the data to be in an order. Then it can use subscription type exclusive or subscription type failover, so that all the events that it is receiving from these partitions are in an order. But there is a constraint that With this type of subscription, you can have at max one consumer for a topic partition. This is because Pulsar need to make sure that all the events that are sent are received in an ordered way. Let's suppose you have other set of consumers, which are your ML workers, which need much more throughput and which doesn't worry about ordering. These consumers, this subscription type can use subscription type shared or subscription type key shared, where let's suppose M0 to M4 is the order in which producer is pushing data to topic partition. Now consumer 1 might be receiving M0 and M3, consumer 2 might be receiving M1, consumer 3 might be receiving M2 and M4. So with this type of subscription, Pulsar will not guarantee ordering of the messages, but you can scale your Pulsar consumers beyond the number of topic partitions that you have. In this example that you have seen, all these three consumers are reading data just from one topic partition. So Pulsar being this unified, Pulsar acting as this unified streaming and queuing model helps us to develop our products based on one underlying system rather than moving our data between RabbitMQ and Kafka based on consumer consumption types. Next, challenges that we have faced in production. Exactly once processing is not an easy thing to achieve. We will discuss how we achieved exactly once processing with Flink-Pulsar connector. Next, Flink-Pulsar connector acknowledgement strategies have improved over time. We'll discuss the challenges that we have faced before and how they got fixed with time. Next, we had to do a lot of open source contributions to Flink-Pulsar connector to add security to this connector to adhere to the Nutanix security policies. And we have also contributed to Pulsar server to run with schemas. One of the lessons that we learned from these open source contributions is that Apache Pulsar is quite open for suggestions and improvements. Every time you open a Pulsar improvement proposal, you will learn something from the discussions. Before understanding exactly once processing, let's understand how Flink does checkpointing. Let's suppose Apache Flink is consuming events from Pulsar, and the order in which it is consuming looks like this. It received message ID 1, 2, 3, 4, and Flink introduced checkpointing. So checkpoint is just like any other event, but Flink introduces itself to the stream. Whenever checkpoint has arrived, Flink will make sure that all the events 1 to 4 are processed end to end and saved to their databases. Once this is done, Flink will persist the local state that it has created till now to DFS and acknowledge to Pulsar that processing for all the messages 1 to 4 are done successfully end to end. Let's suppose checkpointing is done successfully and we kept reading messages other. Let's suppose we have received event 5, event 6, which we are processing, and event 7 is in message queue, which we have to pick it up yet. But meanwhile, your Flink job got crashed. Whenever Flink job restarts, as events 5, 6, 7 are not acknowledged to Pulsar, Pulsar will definitely retry it. And whenever Flink restarts, Flink will make sure that it retrieves the latest data that is attached to the earliest checkpoint that is done. So by using Flink, by using the checkpoints, you will never lose events, and also you will use your local states efficiently. But can you achieve exactly once end-to-end processing with this configuration? No, you have to cross a lot more hurdles. You need transactional syncs to make sure that whenever you initiated a database save on all the events 1 to 4, they are actually saved to your database. Also, let's suppose checkpointing is done successfully and all your data 1 to 4 are saved to your system. Then you have received event 5, which you have processed end to end, saved to your database, and you have picked up event 6 and you are processing. Meanwhile, your Flink job got crashed. As event 5 is not acknowledged to Pulsar, Pulsar will definitely retry event 5. Also, as event 5 is not included in the checkpointing, your local states are also used efficiently. But the point here is event 5 is saved to your database once. As event 5 is processed again, it might not affect your local states multiple times, but event 5 might be saved in your database second time. That's why you need an idempotent system to avoid saving an event multiple times. Next, if you are using complex join operators in your Flink, it might happen that one of the operator is joining multiple streams. In this case, it might receive multiple checkpoints from each stream. In this situation, it might happen that the data that arrived between these two checkpoints might be retried second time by Pulsar. So that's when you need to use barrier alignment, where Flink operator will make sure that it receives the checkpoint from all the input streams before starting checkpoint for this operator. But this will add back pressure on your input stream. With these trade-offs, you can achieve exactly one's end-to-end processing. But from our lesson, what you need to do first is you need to understand your system better and find out what is the processing guarantee that you need for this system. Once you got clarity on what is the processing guarantee that you need, then you can definitely achieve those by using Flink-Pulsar connector. Next, when we started with Flink, we used Flink 1.8. At that time, Flink didn't come up with a default Flink-Pulsar connector. So we used Pulsar Flink connector 2.6.1. It used to do acknowledgements in an suboptimal way, where for every checkpoint, it maintains set of messages which it have to acknowledge to Pulsar. And let's go to the example that we have discussed before. When it has received checkpoint K, there are messages 1, 2, 3, 4, which it needs to acknowledge to Pulsar. So once checkpointing is done, it goes to each of the message ID and send acknowledgement. But at this scale we operate, we get about 10 billion events per a batch. So going and acknowledging each of the messages to Pulsar reduces our throughput as it increases the checkpoint time. When we are upgrading our Flink to 1.15, we found out this new Flink connector Pulsar 1.16, where it is using cumulative acknowledgement for acknowledging messages to Pulsar. So what it does is Flink stores a sorted map of checkpoint ID to a map of topic partition and the latest message that it has received in this partition. Let's suppose checkpointing is done successfully. What Flink does is Flink will pull out all the topic partition to the map, to the latest message ID maps. And let's suppose in the use case that we have discussed before, if it happens that all the events 1, 2, 3, 4 are from the same partition ID, then Flink no need to send multiple acknowledgement requests to Pulsar. It just sends one cumulative acknowledgement to Pulsar, and Pulsar will make sure that all the events before event 4, that is 1, 2, 3, are also acknowledged with this. With this configuration change, we have observed that our throughput has increased as our checkpointing time has reduced drastically. The lessons that we learned from this is Apache Pulsar is a fast growing system. So you need to keep an eye on Pulsar to use the Pulsar at its fullest in your production. Thanks for attending the session. Now we'll open the session for questions. You can even reach out to us personally.